Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and for those of you that don't know me, I'm the director of NITheCS. This afternoon, it's a big pleasure and honor to introduce to you Professor André Weideman. André is a professor of applied mathematics in Stellenbosch, but he grew up academically in Bloemfontein, where he was until 1999, I think. Yeah, after which he moved to the US, first at MIT and then at Oregon State University, where he was an associate professor until he got appointed Stellenbosch University in the Department of Applied Mathematics. André, which I didn't know, in his early career worked on numerical solution of the nonlinear Schrödinger equation, which I will have to read up. So that's very interesting. But today he will speak about a topic that has interested him in more recent times. So André, thank you very much for agreeing to give us a talk. You know how the system works.
So thank you very much.
Talk. Thank you.
So thank you very much, Francesco, for the invitation to speak here. And thanks for all of you who came to be here in person. I know there's also a Zoom stream, but thank you that you are here. I know some people come from afar. The talk is about Fourier essentially and how it applies to differential equations. But first thing I want to say is when you use the word Fourier, it means very many things to different people. Many branches of medicine has a good component of Fourier analysis. Many branches of natural modeling, modeling in the natural sciences, spectroscopy. But I'm not going to talk about any of these wonderfully interesting topics. This talk today is in this very boring lower right-hand corner of function approximation. So I wish I could tell you more about these, but I can't. I'm going to stick to what I know, and that is approximating a function by a Fourier series, of which I'll tell you in a second. So you may have a function, say the blue curve, that you wish to approximate. In this case, the approximant is the red curve. It has some oscillations, which is not good. That's called the Gibbs oscillations, but we'll get back to those. I have to be honest, this was a very hard talk to prepare because I didn't know the audience and I don't know the Zoom or the YouTube listeners. So what I thought I'd do is just to do a 101 tutorial introduction to Fourier analysis, particularly as it pertains to the computational aspects of it. But then even on the second bullet point, I will be getting to some new stuff that'll hopefully be not too familiar for you, and that would be to convert a standard Fourier series into a rational form. In other words, one Fourier series divided by another one. And the question is, what can that gain you? And I'll hope to convince you that that's a smart thing to do in certain situations. Particularly these Gibbs oscillations that I just pointed out, if you do this correctly, by going from a standard Fourier series to a rational Fourier series, those oscillations can be suppressed largely, and I'll show you. And then in the second part of the talk, I will be talking about the application to PDEs. Specifically, if you have a solution computed by Fourier methods, well, maybe you can squeeze another few digits of accuracy if you convert to a rational Fourier series, and that's what we'll talk about. Plus, and then in this last part of the talk, I will be going to maybe more advanced stuff going into the complex plane. So if you are one of those people who think that imaginary numbers do not exist, along with the Earth being flat, maybe this is the part where you can really switch off and do something else. Okay, as I said, I'll be starting at a very low level for my physics and math colleagues. This is the time maybe to take a quick nap or something, because this is old stuff. But anyway, here it is. It can get no more elementary than that. These are the two prime examples of Fourier series that one sees in a first course in Fourier analysis. On the left is a step function. On the right is a sawtooth function. The formulas are given up there. And here are what's called the Fourier series approximations to these functions. Now, your first question is, if we have a formula for these functions, why the heck do we need to expand it in a Fourier series? And the answer is, at least what we're going to do here is, we don't assume that we know the function. We're going to assume that the function is an unknown. And then we're going to take these expansions and have them have unknown coefficients, right? So instead of the 4 over pi, the 1 over 3, and 1 over 5, we can assume an expansion of the form b1 times sine x, b3 times sine 3x, b5 times sine 5x. That whole thing goes into your differential equation. You solve for the coefficients b1, b3, b5, and that way you hope that this reproduces the unknown solution to your differential equation to a good degree. Okay, so even though in these examples the function is given explicitly, keep in mind that in the practice the f of x is an unknown, and we identify it by knowing its coefficients, its Fourier coefficients, so to speak. Right. So these Fourier series, they are expansions in terms of sines or cosines. Depends on whether the function is symmetric about the y-axis, then you pick up the cos terms, or anti-symmetric, then you pick up the sine terms. And of course, you can have mixtures of sines and cosines. But for computational purposes, the key thing is, what do these coefficients do as the number of terms increases? Because why? We would like to use this as an approximation to the unknown function f, but computers cannot sum an infinite number of terms, right? No matter how good your computer is, you cannot sum infinitely many terms. So you have to chop off. And the moment you chop off, you make an error, right? The tail that you're omitting is your error. And the question is, how big is that error? And that is determined by how quickly these coefficients go to 0. So over here, they go to 0 like 1 over n, essentially, 1 over 3, 1 over 5, etc. That's rather slow convergence. In fact, that's pitifully slow convergence. Whereas here, they go to 0 like squares, which is better. And we'll see, well, won't show, but you can see this is tied to the, what's called in math, the regularity of the function. Here we have a jump in the function itself. Here we have a jump in the first derivative. So a continuous function, here is discontinuous, here it's continuous, but with a jump in the first derivative. With each continuous derivative, you pick up an additional factor downstairs, as you can show by integration by parts. And so it goes. So these are examples of slow convergence. How about better convergence? Over here on the left, now we have a series where the coefficients decay like cubes. That's better. And over here is the best scenario of them all. You see now the coefficients go to 0 exponentially fast, 2 to the 0, 2 to the 1, 2 squared, etc. What is the difference between the two? Well, at eyes level, there isn't much difference. But if you look at this, this is a cubic polynomial defined from minus pi pi. And of course, things get periodically extended the moment you approximate them by sines and cosines. This is a cubic polynomial. And if you now look at the second derivative, there's a jump in the second derivative. No longer in the first derivative. That's why we pick up another factor of n, another factor in the power, and we have quicker convergence than in the previous two slides. I find it fascinating that the eye cannot really pick up a jump in a second derivative. To me, that looks perfectly smooth, at least. I don't know about you. But then here, over here, we have a perfectly smooth function infinitely differentiable, and well, analytic, if you know that term from your complex analysis course. So this is the best one can hope for, exponential decay in the Fourier coefficients. So this is where we want to be for computational work. The problem is real life puts us in one of these situations often, right? Nature is kind of spiteful in that regard. It doesn't give us the smooth functions we want. We have to do something to go from a rather non-smooth function or something close to this, where it's computationally very convenient or very fast to compute. Okay, that was my 101 introduction to Fourier series. Let's summarize. I think I said everything here. It requires a truncation of the infinite series. The error is linked to how quickly the coefficients decay to zero. The more continuous derivatives you have, the quicker the coefficients decay. Yes, and the best case are when you have an infinitely differentiable or an analytic function. Okay. Something else about computational Fourier analysis. Why do we use expansions and sines and cosines and not other types of functions? Right? You could also use a power series, a0 plus a1x plus a2x squared plus a3x cubed. If you chop it off, that's a polynomial. Very nice. Why don't we work with that? The key lies in the fact that these functions form an orthogonal basis, which I'm not going to define here. But orthogonal bases are very nice to work with computationally. One reason being they're very stable against round of error, right? If you don't have an expansion, well, you can think of vectors. If you don't have an expansion in orthogonal vectors, well, a little jiggle in the data might cause a big change in the solution. So that's one of the reasons we use sines and cosines. And of course, if your function is in one of these nice classes, like this example number 4 we have here with exponentially decaying Fourier coefficients, then you have superb accuracy, right? Just a few terms in your series gives you high accuracy. And I didn't say that, but I assume everyone understands that the fewer terms you have in the series, the faster your program runs. And time is money in this business. Right. And the last reason why Fourier methods are so popular for expansions is that you have what's called a fast Fourier transform. Now, what this means is the following. Suppose you would have to evaluate such a Fourier series, right? You've computed your B's by substituting it into your differential equation. You found your B's. Now you have to evaluate that, and you wish to evaluate that at n points in your interval. Let us compute how many multiplications would be necessary. Every b times a sine requires one multiplication. We're not going to count the 2 times x and the 3 times x's because those are things independent of the data. You could compute them once and for all. So let's not count those multiplications. Let's just count the multiplications of the b's and times the sines. Well, for each of these terms, there's a b times a sine, so there would be n such multiplications. And if you have to do that at n different points x sub j, well, that's n times n. That's n squared multiplications total. Now that becomes large quickly, right? If you double n, if you double the size of this expansion, your number of multiplications don't just double, they go up by a factor 4, right? So it's a quadratic dependence. So it is a rather expensive way to compute this series if the n is large. But now there's a smart way of doing things. And that was known to Gauss already, but popularized by Cooley and Tukey here in the mid-60s, I think. And that is to use some clever trig identities that can reduce this n squared number of operations to n times log n. And if you recall from mathematics, this log n is a function that grows rather slowly. for most practical purposes, you can just take this as a constant. But of course, there is a certain overhead in doing that. So the typical picture that you have is a direct summation of a Fourier series. The number of operations grows like n squared. That's the parabola, the blue curve. But if you do the FFT, you get something that's much closer to a line. If you think of this log n pretty much as a constant, there you can see it in the graph. And it doesn't matter how big n is, the red curve will eventually win. And that's the big advantage of the FFT and what made it so popular. When I came to Stellenbosch way back when, and I gave my inaugural lecture, I gave a talk on the top 10 algorithms of scientific computing. And FFT was way at the top because of its applicability in so many different areas. Now, I have two pet peeves about the FFT. The one is people use it all over the place. When I Googled some of these pictures that I showed in the beginning, I found a paper that says they're doing FFT spectroscopy. You're not doing FFT spectroscopy, you're doing Fourier spectroscopy, right? The FFT is just the algorithm by which this is implemented. Your picture will look exactly the same if you did the slow computation versus the fast computation. And the other one is there is always an overhead in a Fourier in using the FFT. So for small n, it's better to just do direct summation. And there are so many papers that should be in this world and then use the FFT. The worst example of this I had was a paper that with great fanfare announced a new algorithm that can be implemented by the FFT. And I had to referee this paper. And when I looked at the details, they were just doing that sum for a single value of x. Well, that's just n operations, right? There's absolutely no reason to use the FFT in that case. And that unfortunately, this has become such a buzzword in scientific computing that it's often misused. Anyway, let's move on. I claim that it's convenient. No, not convenient. Useful. Now I'm running in the wrong direction. I claim it's useful if one, we've seen my talk in reverse now. I claim it's useful to convert Fourier series such as this into rational form. In other words, such a series divided by another similar series. First, let us see how that can be done. Let's not do it for Fourier series. Let's do it for ordinary power series, right? So suppose one has a power series such as that, and let's just say we have the first 5 coefficients there, C0 through C4. How can one convert that into a rational function? Well, first off, let us agree that we do not have 6 independent coefficients on the right, because you can always divide by a non-zero constant top and bottom. So one of those isn't really free. So let's, for argument's sake, put B0 equal to 1. Now we have 1, 2, 3, 4, 5 unknowns. And on the left, we have 1, 2, 3, 4, 5 given constants. So we know the C's. So in theory, we should be able to compute the 3 A's and the 2 B's. And indeed, that can be done, and very simply. All you do is you clear the denominator, and then you collect terms in x. X to the 0, x to the 1, x to the 2, etc., until you have enough equations. And it turns out you can set that up as a simple linear system, which coincidentally has a very nice structure, and you can solve for the unknown coefficients. And that's called Padé approximation. Okay, this is Padé approximation for ordinary power series. Here's an example. We know what the Taylor series, or is it the Maclaurin series of the exponential function looks like. So we know all the coefficients. We can do this sort of thing and find at the lowest level, there is a 2 plus x, 2 minus x. This is called a 1-1 approximation because the degree of the denominator is 1, and likewise the degree of the numerator is 1. So this is an approximation to e to the x. If you're willing to include a few more terms, well, if you're willing to go to x to the 5, then you get this approximation and so on. So these are called the Padé approximants of the exponential function. And what are they used for? Well, these formulas remain valid for matrices, right? So if you need to compute the exponential of a matrix, this is what's used in most mathematical software packages. Okay. Of course, it's not as simple as that, but there are other tricks. It's called squaring and scaling and so on. But at the heart of any software package for computing the matrix exponential is this. Right? It's easy enough to compute the matrix powers. At some point, you'll have to compute an inverse or solve a linear system. But there you go. So this is used all over scientific computing. Another example is this one. So on the left, we have a function, 1 divided by root of 1 plus 4x. You can expand that to however many terms you like, because this is just a binomial series, right? 1 plus 4x to the negative half. We know how to expand this using the binomial series. We can convert to rational form, as just described, by solving that system of equations. And now look at what converting to the rational form buys you. The thickish blue curve, that's the original function. In this case, we assume we know the function. That's the blue function. If we stop at the x to the 4 term, that's the power series, that's the cyan curve there. You'll see it approximates well near the origin, but at some point it deviates quite spectacularly, right? Now, if you go from power series to rational, you get the red curve, which, at least on the interval 0 to 1, is pretty much indistinguishable from the function. And I always find this fascinating, and I still don't understand perfectly how it works. You take exactly the same information, those 5 numbers, 1, 2, 3, 4, 5. You stick them into a rational function, and all of a sudden, you get this improvement in accuracy. I will have one slide that maybe gets close to explaining the phenomenon shortly. Not only that, but this Padé approximation can also be used for singularity detection. If you're just given this power series, doesn't matter to how many terms, it's very difficult to extract the location of the singularity, and by singularity we mean where this function becomes undefined, and that's very important in many applications, right? That would be at the point x equal to -1/4, is that right? That's where we divide by 0. If you just look at the power series expansion, there's pretty much no chance of finding that point. Well, you can, if you had your second year math, you can do a radius of convergence. So you know there's trouble somewhere on that circle, but nailing that point perfectly is not so easy. But look, if you go to the rational form, look what it buys you. You just set the denominator here to 0, and you find this, well, the right-hand side is singular, divided by 0. at negative 0.28, which isn't so far off from the actual singularity of the original function. And of course, if we go to the 3, in other words, cubic divided by cubic, then this approximation improves spectacularly. Yeah. Oh yeah. What you're mentioning there is the so-called spurious poles phenomenon in Pade, I think, right? Yeah, that definitely happens. Like here, there's this singularity. That's a quadratic which has two roots. This one has no physical meaning, right? So well, it does have a physical meaning, but it's probably trying to pick out a branch cut. Is my guess here. But you're above the pay scale of this talk now. Okay. Now, so this is essentially, in a nutshell, what we're going to do with differential equations. There are two things at work here. It's improving the accuracy and picking up the singularities where the function becomes undefined. So we're going to do this for differential equations now. Very quickly, what I just described was Pade approximation for power series, such as this one. How do you do it for Fourier series? Well, the key point is that a Fourier series really is just a power series in disguise, because you have these Euler formulas, and by them you can go from the real sines and cosines to the e to the ix's and e to the minus ix's, and then if you put z equal to e to the ix, then the e to the 2ix will be z squared and z to the 3, and that's how you pick up your power series. And so you just convert from Fourier series to power series with a simple transformation, z is e to the ix, and that way you can do pretty much what we just described to convert your Fourier series into a rational Fourier series. So for example, if you have this Fourier series, if you convert to rational form, there you have, well, at lowest level, it would be this Fourier series divided by this one. At the next level, it would be this one divided by that, and so on. Okay. So, let's return to that Gibbs phenomenon that I mentioned earlier. These oscillations that appear when a discontinuous function is approximated by a Fourier series. In this case, we have a jump discontinuity. So it's like a sawtooth function. And if you keep cranking up the number of terms, these oscillations get squashed towards the point x equal to 0, but they don't really go away. There's an overshoot, and that overshoot is about 8.9%. That's a very famous number in Fourier analysis. It's actually worked out explicitly by this formula. It's called the Gibbs-Wilbraham constant. Yeah, and that's a consequence of the fact that the function is discontinuous and the Fourier coefficients go to 0 very slowly, like 1 over n. Now, if we convert to rational form, look at what happens. On the left now is that same a sawtooth function that we're trying to approximate. Now we have a very large number of terms, 2048. The overshoot sits there. That's the blue spike up there, the 8.9% overshoot. But if you go to rational, you can't see it on this scale. You only see it when we zoom in. Now we've zoomed into a tiny region about the origin. You see, going to rational suppresses the Gibbs oscillations, aside from a very tiny blip, quite close to the x equal to 0, quite close to the discontinuity. I wish I knew what this overshoot is. It's like 2.5% if one computes it numerically. But as far as I know, there's no formula for it. So I really would like to know what that number is in the same sense as the Gibbs-Wilbraham constant is known. But I don't. I have a few ideas that I might pursue, but so far nothing. Okay. Yeah. So this is my my first complex slide, and which is where I tried to give some explanation of why going to the rational form helps to improve the accuracy and suppress the Gibbs oscillations. And that is the following. The function that I've depicted there is related to this one, sine kx divided by 1 over k. If you sum this explicitly, you can do that, and you find that it's given by these difference in these logs. Now, what we're doing is then, if we approximate that by rationals, we're approximating the logs by rationals. And for those of you familiar with complex analysis, will know that the log has a branch cut. This, by the way, is a picture of the complex plane. Right here on this side is the sawtooth function that we're trying to approximate. What the rational approximation does is it now introduces singularities into the approximation, much as what happened in this example where we got singularities introduced. What the rational approximant here does is it puts a bunch of singularities on what's called the branch cut of the logarithm. And those try to mimic the jump in phase across the imaginary axis. So in some sense, these nearest poles try to mimic the jump behavior in the function, and that is how the Gibbs oscillation is reduced. Not completely annihilated, but reduced. Apologies, but that's the best I can do in terms of describing this in a one slide exposition. Okay, now PDEs. And our basic example would be the Burgers equation, which is this one here. So these are time-dependent PDEs. So U is a function of both x and t, space and time variables. We're using the subscript notation for partial derivatives with respect to t, and likewise partial derivatives with respect to x. So Burgers equation is an equation that models the interplay between nonlinearity and diffusion. So the U times Ux, that is a nonlinear convection term. On the right-hand side, we have the diffusion term. There's a diffusion coefficient multiplying the second derivative. Now, if we, for the moment, ignore the nonlinear term, just cross it out, that's then the heat equation, which is coincidentally what brought Fourier to Fourier series, right? Originally, right. And what that does is it, as the name suggests, it diffuses, so energy dissipates, so everything gets forced down to constant steady state. That's what the right-hand side does. what the left side, what the nonlinear term on the left does, it focuses, it causes things to steepen, the profile to steepen. So here we have what happens when we start an initial condition, in this case just negative sign of x, with the Burgers equation. At first, the nonlinearity dominates, so the solution profile steepens, 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 but then the diffusion term kicks in and everything is just squashed down towards the zero steady state. In this case, nu is not too, I don't know what nu is, maybe I didn't write it down, maybe 0.01. If nu is zero, perfectly zero, then at t equal to 1, there would be what's called a shock. That's where the solution becomes multivalued, right? And that's where the physics breaks down. But as long as you have diffusion on the right, no shock ever appears, and so it's a perfectly well-defined single-valued function all the way through. However, if you look at this picture and you squint your eyes, it is just that one, right? Give or take a few poetic freedoms. So the question is, if we solve this numerically, and we find that we don't have very good accuracy here because we're very close to the Gibbs situation, right? Can we go to a rational form and squeeze out better accuracy? And that's precisely what we can do. How do we solve such equations numerically by Fourier methods? Well, very simply, we assume a Fourier series expansion, and now we have the complex form of the Fourier series, so we replace the sines and cos with the exponents, the complex exponentials. What you do is you simply plug it into the PDE, and then you collect the coefficients, and of course you have to truncate, but then you have a dynamical system for the evolution of the coefficients of the Fourier series, right? If decay, those would be the Fourier coefficients of the u squared, and you can compute that by an FFT convolution. And then, you know, a derivative with respect to x will bring out an ik factor. A derivative with respect to two derivatives of x will bring out an ik squared factor, and so on. Right, so you just feed this to your favorite ODE solver. I've just used MATLAB ODE 15S. And then now you have the coefficients at any time you like, and you can do things with them. You can convert to rational form to either improve the accuracy or to see what the singularity structure is in the complex plane. Right, so for example, here is the very picture that I showed you in the beginning. This one at time t equal to 1. And somehow get Beethoven in the background. I wonder why. It's next door or something. Maybe it's anyway. So there is the profile quite close to the breaking. What is the accuracy? If we plot the pointwise accuracy, it's not very good. It's like 10 to the minus 5. Maybe for your application it would be good enough, but how can we squeeze out more accuracy? Well, we just go to the rational Fourier case, and now the errors are on the order, these would be the red errors, on the order of 10 to the minus 14. Here at the very close to the point of breaking, there the accuracy hasn't been improved that much, maybe just a gain of 2 orders of magnitude. But down here, away, there we have a gain of accuracy of about, what, 10 orders of magnitude or so. Okay, Yeah, the question is, what does it cost? Because nothing is free in computational work, right? You cannot get this gain in accuracy for nothing. Well, we saw that going to the complex form, you solve a linear system. So that's the extra work. But in order to get to this point, the integrator of the ODE system already did some 12 linear system solves. So there's just one extra that you have to do. So that's less than a 10% extra computational costs that you have to do. So very little extra effort. It's almost the closest you'll get to a free lunch in numerical work. Okay, and then on my last topic is this business of computing pole dynamics in the complex plane. There again, we have the phase plane, and now I want you to imagine. I actually have a little MP4, but since I think I'm running out of time, I'm not going to show it. What is we have this. We have this behavior on the real axis of the solution of Burgers' equation. What does that look like in the complex plane, right? And we can use adaptive Fourier to go into the, not adaptive, rational Fourier, to go into the complex plane. And this is what we see. There are what's called poles that drives the dynamics on the real axis. Now, we started off with a function that was minus sine x, which has no singularities, right? That is what the complex analysts would call an entire function. There are no singularities. But the moment time starts, these singularities are borne out at infinity. They come marching along the imaginary axis. Now, as they get closer to the origin, this profile steepens, right? This is during the steepening phase of the Burgers equation. They reach a closest point to the real axis, and then they turn around and start marching out. And as they march out, the solution becomes flatter and flatter and eventually falls flat. So there are two phases in the dynamics. Poles moving in corresponds to the nonlinear term steepening the profile, and then as diffusion eventually wins the battle, the poles just turn around and retreat. Like I said, I have a little animation of this, but I don't think it's necessary. Everybody can imagine those poles running in from infinity and walking back out. Of course, there's another set down here in the lower half of the complex plane. So it's two sets of poles coming out and doing that. But I didn't show the bottom ones because it's just symmetric. Now, what do we do? What happens if we go from diffusion to dispersion? And since this I thought would be a predominantly physics crowd, I included complex diffusion, which leads us to a Schrödinger term on the right. I resisted the temptation to call the coefficient nu h bar, because this isn't quantum mechanics. This is just a model for combining nonlinearity and diffusion, dispersion now. So what happens is now this. Again, initially, the nonlinear term dominates, steepens the profile, trying to force it to become a shock. But then when the profile is steep enough, this right-hand side kicks in. And now dispersion doesn't have the same effect as diffusion, as flattening things out. It spreads things out into wave packets. And then you see this sort of business appearing. Okay, now What does this look like in the complex plane? By the way, of course, now we have a complex valued u the moment you have a complex diffusion coefficient. But I just plotted the real part, the imaginary part is similar. What does this look like in the complex plane? Well, this is what it does. Again, you have poles. This is the same initial condition as before, the sine x, with no poles on the finite, in the finite domain, but they're born at infinity. They run in. But now dispersion causes them to drift off the imaginary axis. And that's what causes these oscillations, right? So you can associate those wave packets, right, with poles that has drift off the imaginary axis, and as time goes on, they line up almost parallel with the real axis. And then there's a very complicated interaction between all of it. Of course, they cannot run through each other because that would violate the local singularity analysis of the equation. So they bump off each other. Really fascinating behavior, but very complicated to describe. By the way, this isn't the nonlinear Schrödinger equation that was mentioned earlier. Nonlinear Schrödinger equation would have a different kind of nonlinearity there, right? Typically cubic. So this appears in the literature, but is not that very well known. I just thought I'd include it here for this audience. And then very lastly, there's a very famous equation in this family, almost as famous as Burgers, and that's the Korteweg-de Vries equation. And it has this very special property that it combines nonlinearity and dispersion in a very special way, in the sense that it is possible for those two operators to be in perfect balance, so that you don't get the steepening effect of the nonlinear term, and you don't get the spreading out term of the dispersive term, but they're in perfect balance, so they can keep a wave profile intact without any change in shape. And that's called a soliton. The first one is a single soliton, just translating from left to right. The other one is a two soliton interaction. Many of you have seen these pictures. Very famous discovery in the mid-1970s or so, early 1970s. A very famous person in this area is Kruskal, Mount Kruskal, and he said one could understand the phenomenon of soliton interaction if you view it as a parade of poles in the complex plane. And that sort of tickled my mind, and I said, why not compute it then in the complex plane? In 2019, I was invited to a conference in Valencia, and I thought I would do that. And I'm still very proud of this, and this is my last slide. So over there on the left, that's the original picture that Zabusky and Kruskal published in Physics Review Letters, where they announced the the phenomenon of a soliton. They started off pretty much with a sine initial condition, just like I did. But this is the eventual picture they showed after time has evolved for, I don't know how many seconds. Oh, maybe the initial condition can be seen somewhere there. But anyway, this initial profile, the sine profile, breaks up into a number of these solitons. In fact, they identified 8, I think. There they are. And this, as I said, this is as an iconic picture as there is in applied mathematics. So I thought I would tackle that and take it into the complex plane. And here is what I did. I just translated it. Their domain is 0, 2. I just translated it to -3, 3. So just doing the right rescalings to get it in the right form. And this is what you get when you go into the complex plane. Over here on the real axis, you see the various wiggles in the Sobuski-Kruskal picture, and there you see the poles as they set out in the complex plane. They're not nice round towers because if you look at the scales, I couldn't go too far into the complex plane. Very hard to compute this. Took a lot of computational time and so on. Other features that you may or may not be able to notice is that the colors in the phase go around twice. So these are poles of order 2, not just poles of order 1, which adds another complication. The moment you have multiplicities in numerical computations, it's hard to compute. But I think I'll stop there, aside from mentioning that this has appeared in a paper in the proceedings of the Valencia meeting, the ICAO meeting of 2019, and you can read it there. Thank you very much.
Yeah, thank you very much for a very nice and interesting talk. I think it was perfect for a NITheCS Colloquium. Very much.
Thank you.
The questions, Professor Weideman. I know there is one question online, and maybe let's start with the real questions, and then we move to the virtual ones. Sorry, you can.
Hi, can you hear me? Yeah.
Yes, yes.
Thanks for the talk. I had maybe a basic question about when you had the example of the Padé approximation.
Yes. Let me get it. That one.
Yeah, this side. So just to clarify, so the Padé approximation is a rational approximation of an analytic function about a point, right?
Right.
So because I was looking at, because if you obviously take the limit of x goes to infinity of the approximation, it's not going to capture.
Oh no, absolutely not. No, this is at 0. I should have said that. It's so the Padé approximation is essentially the equivalent of the Taylor series, or is the Maclaurin series? I always forget which one is based at 0.
Okay, yeah.
Yeah.
I just wanted to check.
Definitely.
Like it was
Definitely.
valid. So it's about a point, yeah.
It's about a point, yeah. I should have said that. Thanks.
Are there more questions? Over there. Yeah, please.
Yeah, yes. Thanks a lot for this nice talk. So how easy is it to actually apply these to other soliton-like models, like, for example, the Sine-Gordon or the kink model in there? The kink, it's non-integratable. It's in that sense more interesting because you're, in addition to the bouncing solitons, you also get some fluctuations in the field. And the question would be whether you can find some interpretation, not necessarily, but some explanation for example, the bouncing of kinks and things like that.
That's very interesting. Very interesting. I haven't looked at Sine-Gordon in this paper that I've cited right at the very end. I've included my favorite equation, the nonlinear Schrödinger, and there are breather type solutions. You see the poles going out and coming back in, and that causes the breather kind solutions. Now those are integrable equations. If you go to non-integrable, I don't know. Of course, it all depends on the equation. I found Burgers and Nonlinear Schrödinger rather easy to compute. For some reason, KDV is very hard. KDV, I obviously didn't show the evolution from 0 to this point, but it's very hard to compute because initially it looks like it's poles of order 1, which cannot be because the equation doesn't support such things. But and people who does perturbation analysis tells me it's the same thing. If you do naive perturbation analysis, you get poles of order 1, which isn't correct. So you should do a rescaling. So the numerics picks up the wrong type of pole. So it's problem dependent, but I'd love to talk more about the particular equation that you've mentioned.
Then I take advantage of having the microphone. So at the beginning, someone mentioned that these Padé approximations are also used for finding exponentials of matrices.
Yeah.
aren't there any ordering ambiguities then? Because then you now have one matrix and you have to multiply it by the inverse of another matrix. And
That
so that form.
um, oh, come on.
There
There you go.
there you have a matrix in the numerator and a matrix in the denominator. So you probably would write the matrix in the denominator as the inverse of.
Correct.
Then don't you have
That would assume that matrix is invertible to
that's
start
the
with,
first
right?
point. And even if it is, so do you multiply it from the left or from the right? Do you have order?
Oh, yeah. Good question. You multiply from the left, as far as I know. But yeah, this was just in passing. This is definitely at the heart of any software for computing the matrix exponential, but the details is not as simple as I make it out to be.
Thank you.
Donovan, I think there was a question on, okay, one more real question, and then we move to the virtual questions.
Hi, thanks for the talk. So this is tangentially related. You mentioned the fast Fourier transform, and I know that in image processing and especially in radio astronomy, we love using the discrete fast Fourier transform to process images of the sky and so on. I was just wondering if you could provide some insight as to just how accurate these discrete fast Fourier transform algorithms are, and how you would sort of compute like the error margin.
Oh, yeah.
Choose like your bins in your Fourier
Right.
modes. Thanks. Thanks.
I'm slightly confused by the term discrete fast Fourier transform, because fast Fourier transform only operates on the discrete situation. So how shall I put it? Let me try and do it like this. If I cut off that J and make it X, that would be a continuous Fourier series running to infinity.
Right.
The moment we discretize it, oh, there's a J missing in the first one, I'm sorry. Right, there should be a J there. That would be a discrete Fourier series. Now we've truncated it. We truncate the series and then we evaluate at certain points. That's a discrete Fourier series, and that can be implemented by the fast Fourier transform. And the difference between that and the first one is, again, how quickly these coefficients go to zero. There is what's called an aliasing formula that relates the difference in the coefficients of the discrete one, and the continuous one. And it pretty much says that the Fourier coefficients, the discrete Fourier coefficient, if you compute it by a discrete formula, is equal to the Fourier coefficients of the continuous one, but with alias terms added.
Okay, I get you. Yeah, that sort of answers my question. So
If you Google aliasing formula, it'll answer your question.
okay.
So it all depends on how quickly those coefficients go to zero again. It's again that same question. How quickly do the coefficients go to zero? If they go to zero rapidly, your approximation error will be small, and otherwise it will be not so
Okay,
small.
yeah, that answers my question. Thanks.
Okay, so there's one online question here. Do we have a general procedure to transform the Taylor series to a rational form?
What I described here is Padé approximation. That would be a general series, a general formula, but that's not the only formula, right? There are other ways of converting, say, a power series into a rational approximation. There is these days very popular what's called a AAA algorithm for doing that, and so on. Yeah. So as far as Padé is concerned, that's a general, well-developed theory, but it's not the only one. Not sure if that answered the question.
Okay, if there are no more questions, then Professor Weideman, thank you so much again for a very nice talk. And thank you to the real audience and the virtual audience.